Good morning, good afternoon, good evening class. This is Mr. Arocena, and on today's video we're going to be talking about resistors in series and parallel circuits. So let's go have an introduction into what series and parallel circuits are, and hopefully you guys remember what they were from our early studies in Science 9. Alright, so resistors in series. A series circuit is a circuit that offers a single path for the electrons to travel in. The current remains the same in all throughout the entire single path. Okay, that's what characterizes a series circuit, is that the current remains the same through all the resistors. The rule here is that the voltage across each resistor has to add up to the terminal voltage of the battery source or the power supply. Okay. So V1 would represent, this would be voltage at resistor 1, voltage at resistor 2, voltage at resistor 3, and so on. So basically what happens is that the terminal voltage of the battery gets split up between the resistors. Now, if you remember from Ohm's law stated the following, that the voltage is equal to the current in the circuit times the resistance. So by substituting Ohm's law into here, we can get the following, that the total current, so we'll say total current times the total resistance must equal the current in resistor 1 times resistor 1 plus the current in resistor 2 times resistor 2 plus the current in resistor 3 times resistor 3, and so on. Now, because there's only one path, the current has to be the same throughout that path. So current in resistor 1 has to be the same as current in resistor 2, which is the same as current in resistor 3. So mathematically what we can do is, because all of these currents are the same, we can just divide them out. So the currents all divide out, and we are left with the following, where the total resistance is equal to basically just the sum of all the resistances added together. So this leads us to the following simplified equation, where the equivalent resistance in the series is as follows. So total resistance in series, and this will become very important as we analyze circuits later on, especially more complicated ones where we have series and parallel circuits altogether. Now, let's go to an example of working this out with a circuit that does not have the current installed or current given to us. Alright, so example 1. Here's a circuit diagram, and we're asked to calculate the total resistance and then what is the current in this circuit. Alright, so here's our circuit. So we know that our total resistance, let's call it RT for total resistance, is going to be the sum of our resistances. So we have our 3 kilo ohm resistor plus the 10 kilo ohm resistor plus the 5 kilo ohm resistor. So altogether the total resistance in this circuit is going to be 18 kilo ohms. Okay. Then to calculate the current, well, we know the current is all the same, so we can just use the following, where we get the terminal voltage or total voltage is going to be my current times my total resistance. Rearranging this, we get the following. Current is going to be total voltage, or terminal voltage, divided by total resistance. Battery has a terminal voltage of 9 volts. Something we'll make note is that this will assume is going to be the terminal voltage, because we don't have any information about the internal resistance of this battery, so we'll just assume it's 9 volts. And then divided by the 18 kilo ohms, get the following, where the total amount of current, 9 divided by 18, this will be 0.5, and this will be in amps, being a current. So total current flowing through this circuit is 0.5 amps. Alright, so there you go. So remember, for circuits in series, the total resistance is just the sum of all the resistances added together. Alright, now parallel circuits, they are different in that parallel circuits or parallel resistors, there's multiple paths for this. And the current in each path is going to be different, which means, well, it doesn't mean this, but one of the neat consequences of this is that the voltage across each path is actually the same as every other path. So that's kind of the difference here. In series, so I'll make a note here. In series, current is the same in the path. Because there's only one path, so the current has to be the same. In parallel, it's the voltage in each path is the same. Okay, so this leads us to the following relationship with resistance, where the resistance is kind of a weird inverse relationship. So this is my total resistance in parallel. Total resistance in parallel. So the 1 over the total resistance is going to be 1 over R1 plus 1 over R2 plus 1 over R3 and so on. Alright, so let's go through an example of how to calculate the resistance in a parallel set of resistors. So here we're going to calculate the total resistance in the circuit below if each resistor is 10 ohms. So we have a 10 ohm resistor here, a 10 ohm resistor here, and this is also 10 ohms, and this is also 10 ohms. Okay. This looks slightly complicated, but it's actually not that bad if you break it down into simpler problems. Alright, so when you calculate these types of problems, it helps to sort of identify what parts of the circuit are in series and what parts of the circuit are in parallel. Because then we can use the series rules for the series sections and the parallel rules for the parallel sections. So for example, here, these two resistors are in series with each other, so we can sort of call that an equivalent 20 ohm resistor, because they're in series, so we can just add them together. Similarly, these two down here are also in series, so we can add those together. So we get a 20 ohm resistor there. Let's finish the different circuit diagram now. So now our problem, rather than having 4 resistors, we can basically simplify it to a problem of 2 resistors, where each resistor now has the top pair of resistors has a total resistance of 20 ohms, and the bottom pair of resistors has a total resistance of 20 ohms. Now these two resistors are in parallel because there are 2 paths. So I'll highlight the 2 different paths. So one path here and one path there. So that's how we can sort of identify whether it's a parallel or a series circuit. Is if I have a current flowing into here, I now have the current can go either this way, or either this way, or the current can go this way. So that branching path signifies that this is now a parallel section. Being a parallel section, we can then calculate the total resistance as follows. So the total resistance is going to be 1 over R1 plus 1 over R2. So we'll carry out the calculation. 1 over total resistance is going to be 1 over 20 ohms plus 1 over 20 ohms. Carrying this out, this will become 2 over 20 ohms. This is 1 over total resistance. Simplifying that fraction, we get 1 over total resistance is equal to 1 over 10 ohms. And then because we can basically just flip this, so we get total resistance is going to be 10 ohms. There we go. There's my total resistance. So in parallel, the total resistance actually ends up being smaller than the sum of the resistors that are part of the parallel circuit. So this next example will showcase what will happen if we have resistors that are both in series and in parallel. Okay, so here all the resistors are 10 ohms to make things a little easier for us, and the source voltage is 5 volts. What is the current in this circuit? Alright, so what we're going to do is kind of the same thing we did in the previous problem, where we will take the resistors that are in parallel and treat them as a pair of parallel resistors, and we'll take the resistors in series and treat them as a pair of resistors in series. So for example, let's start with these two. These two resistors are in parallel, so we can calculate their equivalent resistance. So total resistance here will be 1 over, and they're both 10 ohms. This this ends up being 2 over 10 ohms, which ends up being 1 over 5 ohms, and this will be total resistance, and then we just flip them, so total resistance will be 5 ohms. I'll make a note, this is 5 volts, or 5 volts. Alright, now once you've calculated total resistance, we can then simplify this problem to look like this. We have our battery, resistor, and that pair of parallel resistors can now be reduced to a single resistor like that. Now all three of these resistors are now in parallel. So this is R1, this is R4, and this is the result of, let's call this 5 ohms. And they're all in series, so now the total resistance will just be the 10 ohms plus the 5 ohms plus the 10 ohms, and this will end up being 25 ohms. So now we can break this problem down to basically a single resistor. So with a value of 25 ohms. Now we can calculate the current using Ohm's law, V equals IR. So current is voltage over resistance, and the current voltage was 5 volts. We have a resistance of 25 ohms, so our total current will be 0.2 amps. So no matter how complicated your circuit is, you can always break it up into pairs of parallel or pairs of series. This is kind of how I would highly suggest you approach more complicated circuits, is look for a pair of circuits which are either in parallel or a pair of circuits which are in series, and then you can just deal with them that way. And as you find equivalent resistances, you can simplify the diagram like we did here. Here we replaced the parallel circuit or parallel resistances with a single resistance, and we just simplify further. That's how I would suggest you handle any kind of circuit diagram resistance problem like that. It's just simplify and simplify and simplify. It might take a lot of space, but it's as long as you take it one pair of circuits at a time, or one pair of resistors at a time, it shouldn't be too difficult. So your assignment then for today will be as follows. You can complete, those are more practice with Ohm's law and circuit diagrams. And if you guys have any questions, you guys know how to contact me.